Yesterday you watched a video that was titled Thermochemical Equations. With that, I'm adding in a little bit something that's called specific heat. So, our learning target is the same one that it's been for, I don't know how long. Okay. Oh, actually, no, this is a new one. We need to write and interpret thermochemical equations and use them to calculate the changes in Gibbs free energy, delta G. So, we're going to use these thermochemical equations, okay, to help us with the free energy calculations. Now, our success criteria. We need to be able to distinguish between an exothermic and endothermic reaction. Whether heat is given off, whether heat is taken in. We need to be able to calculate the heat absorbed or released in a chemical reaction. And finally, mathematically relate the heat flow to specific heat, mass, and change in temperature. An exothermic reaction. I think I took this slide directly from the video. An exothermic reaction is a reaction that releases energy in the form of heat. So as I'm looking at this equation, I have two reactants. Solid carbon reacts with oxygen gas to give me carbon dioxide gas, and this plus 393.5 kilojoules. That is the amount of energy that is released, and that energy is released in the form of heat. Okay? That energy is released in the form of heat. You're all right. Now, notice where that is at the reaction. It's on the right-hand side of an arrow. So what side of the reaction is that on? The product side. Keep that in mind, because when we have the heat on the product side of the reaction, it is exothermic. It is being released. Now, as I look at this equation, my endothermic reaction, this isn't a reaction when heat needs to be absorbed. So I have calcium carbonate right here as a solid. I need to add 178.1 kilojoules of heat, and then it will decompose into calcium oxide as a solid and carbon dioxide gas. So, if I don't add this amount of heat, will that reaction ever occur? It will not. Notice that heat is on what side of the reaction? The reactant side. Okay? So the reactant side tells me it's endothermic. I need to have heat added, or that is not going to happen. Now, this specific heat right here, ladies and gents, Q equals Cp, which is the specific heat, M, which is the mass, delta T, which is the change in temperature, will give us the heat lost or gained. Does that look familiar to you? It should. Where have we seen this equation? The freezing boiling point, specifically when we were doing the 5 different areas of energy changes when we had phase change, right? 1, 3, and 5 all dealt with mass, the specific heat of water, the specific heat of ice, the specific heat of water vapor, and the change in temperature. So you are familiar with this equation. That's why we're not going to spend a great amount of time on specific heat here, because we've done these calculations already. We're going to work a couple of problems, okay? 3 of them to be exact. And here is our first one. Go ahead and copy this one down. and then we will work it. The problem states if 200 grams of water is to be heated from 24.0 degrees Celsius to 100 degrees Celsius to make a cup of tea, how much heat must be added? The specific heat of water is 4.18 joules per gram times degrees Celsius. Now, as I said, we've dealt with these before. So when I put my equation, Q is equal to the specific heat times the mass times the delta T. Now, when we were dealing with this, we flopped the specific heat and the mass. We had the mass first. Does it matter what order you put them in? It does not. Does not. So what I'm going to do is I'm just going to simply take the specific heat of water, which is 4.18 joules per gram times degrees Celsius. I'm going to multiply that by my mass. I have 200 grams of water, and my delta T is my change in temperature. My final temperature is 100 degrees Celsius. My initial was 24, so that tells me that that is 76.0 degrees Celsius. So when I take and I multiply these three together, I take the 4.18, I multiply it by 200, and I multiply it by 76, and I get a value of, I get a value of 63536. Now, what's my label going to be? My grams cancel, my degrees Celsius cancel, so that's going to leave me with joules. Now, I have not sig figged this yet, so I need to go back up and I look. 200 is 3 sig figs because of the decimal. 3, 4, 3. I have 3 significant figures. So my answer needs to have 3 sig figs. Here are my 3 sig figs, and I need to put in 2 placeholders. So the amount of energy needed to heat up that cup of tea is 63,500 joules. Nice and easy, like I said. We've done that before. Now here, go ahead, not this one, not this one. Yeah, this one. Go ahead and copy this one down because this is a little bit different. We're going to have to manipulate our equation. What is the specific heat of a substance that absorbs 2,500 joules of heat when a sample of 100 grams of the substance increases in temperature from 10 degrees Celsius to 70 degrees Celsius? Mental note, I see that I have 2 sig figs because my 2,500 joules is only 2 sig figs. So when I get finished, I'm going to sig fig this to 2 digits. Now, I have my equation, and I'm going to have to manipulate it. Q is equal to the specific heat times the mass times the change in temperature. Now, I'm trying to calculate the specific heat of the substance. So what I'm going to do is I'm going to divide both sides by the mass times the change in temperature. When I do so, I get a cancellation on this side. So my equation now is going to be the specific heat is equal to the energy, Q, divided by the mass times the delta T. As I go back into my problem, I stated that my energy was 2,500 joules. My mass was 100 grams, and my change in temperature, my temperature went from 10 degrees to 70 degrees, so my change in temperature was 60.0 degrees Celsius. Now, when I do this calculation, okay, I take my 2,500, and I divide it by the product of 100 times 60.0. And when I did so, I got a value of 0.41666 repeating. Now, I stated earlier that I had 2 sig figs, so when I 2 sig fig this, my specific heat is going to be equal to 0.42, and I need to get a label. Well, does anything here cancel? It does not. So my label is going to be joules over grams times degrees Celsius. And if you remember from the previous problem, that's what the specific heat was in. Questions on that? Now here's our last one. Go ahead and copy this down. This is not our last one. This is our last one. Go ahead and copy this one down, and we will work it. Granite has a specific heat of 800 joules per gram times degrees Celsius. What mass of granite is needed to store 150,000 joules of heat if the temperature of the granite is to be increased by 15.5 degrees Celsius? So my change in temperature is already given to me. It's at 15.5. So what I'm going to do is I'm going to manipulate my equation to solve for the mass. So what I'm going to do is I'm going to divide this side by the specific heat times the change in temperature. Well, what I do to one side, I have to do to the other. So I'm going to divide it by specific heat times the change in temperature. This side, those cancel out. So I'm going to get a new equation. I'm going to get a new equation that my mass is equal to the heat divided by the specific heat and the change in temperature. So I know that I had 150,000 joules. My specific heat for the granite was 800 joules per gram times degrees Celsius. My change in temperature was 15.5 degrees Celsius. So as I look, my joules is going to cancel, my degrees Celsius is going to cancel. Grams in the denominator of the denominator is going to make it my label be in grams. And when I divided that out, 150,000 divided by the product of 800 times 15.5, and I came up with a value of 12.097 grams. When I look at my sig figs, I can see that I need to have 2 significant figures. So my mass is going to be equal to 12 grams of granite is needed to store that particular amount of energy.